Thank you very much for having me today. My name is Czekala, I'm a graduate student. I work on young stars and their protoplanetary disks. Today I'm going to be talking about two techniques we've been working with to measure the properties of the stars using both the optical stellar light and certain stellar disk itself. And interestingly enough, this is actually my first conference where there's been an official Twitter hashtag, so please feel free to tweet at me, I guess, if you want. So all astronomers are familiar with the Hertzsprung-Russell diagram. The striking feature of this plot, of course, is the main sequence, where most stars spend most of their lifetimes. Their position along the main sequence is primarily a function of stellar mass, with more massive stars being brighter and hotter. So I'd like to answer the question, what path do stars take as they are born and first evolve onto the main sequence? What are their properties before they actually join the main sequence? To do that, let's just select the subsample of stars here and zoom in. And these are stars around the mass of the sun or a little bit less massive. And after about 200 million years, all stars are pretty much on the main sequence, and this is where they'll stay for the rest of their life. When they're first born, they're brighter and bigger in size and a different part of the diagram. And as they contract and start to begin, so I'll meditate on the HR diagram. As they evolve, they make their way from their starting locations back onto the main sequence. You can see that stars with different masses take different paths throughout this diagram, with more massive stars making their way quickly to the main sequence, with some of the tiniest stars taking a very long time to actually begin nuclear fusion. So the paths of these stars is a fundamental underpinning of a lot of astronomical research, everything from the IMF to stellar clusters to how do your planets evolve. So actually understanding these paths accurately is a fundamental part of doing astronomy. So my thesis work is designed around figuring out ways to measure stars with properties in this region of the HR diagram in order to calibrate these models. So I do this using two types of methods and two types of data sets. The first is a protoplanetary disk. Since these stars are young, many of them still host a disk that's rich in gas and dust and is eventually the site of planet formation. And using radio interferometers, we can study the motion of this disk and actually derive a precise constraint on the stellar mass. Also, we use optical and infrared spectrographs to obtain high-resolution spectra of the star to obtain properties like how hot the star is, how big it is, and what its composition is. So these are two complementary approaches designed to study the stellar properties. So how do we use the disk to actually determine the stellar mass? Well, first we come up with a model of the disk properties as a function of 3D space. This specifies the gas temperature, the density, and the velocity, which is primarily a function of the central stellar mass. Then we run a radiant transfer code and come up with a model. How would you actually study the motion of the disk, though? You would use, so we use a radiant interferometer where you can actually obtain exquisite angular resolution to actually resolve the structure of the disk. And if you do that focused around a narrow spectral line, frequency, say, like that of carbon monoxide, you can actually see the spectral line redshift and blue shift and reveal the kinematic fingerprint of the disk itself. Here I'm showing channel maps, so these are images as a function of frequency. On the left, you have blue shifted emission, so the emission coming towards you. On the right, redshift emission going away from you. For a disk, much like the observer is looking at there, kind of at a 45-degree angle. So I'm going to play a little movie where I'm going to change the inclination of the disk to face on, to edge on, and I'm going to change the mass of the star. You can see how this fingerprint changes. So if we go onto a face-on disk, most of the emission is essentially concentrated. Go back to an edge-on disk, you can see things in profile. Now we'll go back to a 45-degree disk. If you go to lower mass, you can see that the emission is more centrally concentrated. It's not as high velocity. As you go to higher mass, you can see that there's more emission in line tails at higher velocity channels. And so this is kind of a complicated model that involves a lot of radiative transfer and Fourier transforms to fit to the interferometer. But the point is that when you actually model these disks, you can derive an extremely precise constraint on the stellar mass, because now you're doing both astrometry and radial velocity monitoring of test particles, millions of them are circling around your central stellar mass, and your model can be highly constrained. So this is my first technique, which we use to actually dynamically weigh potentially single stars in their earliest years before they make their way towards the main sequence. And due to ALMA sensitivity, this technique will actually be open to a wide range of single stars, where we can begin to assemble a statistically significant sample of young stars. So the second part, which I'd like to talk about, is how do we use stellar spectroscopy to determine the stellar properties. Here's a spectrum of a star that's slightly hotter than the sun, and you can see that there are many absorption lines. So if you're going to determine the temperature and the radius of the star, traditionally what you do is have a model that predicts the spectrum as a function of those parameters. Now, what's traditionally done is you select a couple hundred lines which you think you understand very well and can study in great detail. John Brew is going to talk a lot more about this after me, and I think this is an excellent line of work and is really commendable in a way to really get very precise estimates of stellar properties. But I'd like to try to address the question that instead of just choosing lines that we understand, what if we move into the realm of actually trying to fit the entire data set? So instead of just a region of the spectrum that we understand very well, what happens if we try to fit, say, the whole entire optical spectrum in high resolution? So there's some more problems that we have to deal with when we move into this regime. In particular, the models that predict the full spectrum are amazing. I mean, you can see that the model matches this data set quite well. But the problem is they're not perfect. And that not perfect part means you have to make different assumptions about your types of statistics that you use to actually fit model to data. And so our work is we developed an alternative likelihood function instead of chi-squared. I'll just give you a taste of that in the next slide. So I'm going to focus in on a region of the residual that includes both one of these sharp spectral lines and kind of a continuum itself to give you a taste of what's going on. That's down in the lower left there. So if you're fitting a model to data and you think your model fits well, a good test is to try to generate noise from your noise model and see that the residuals of your fit actually sort of look like the noise. Otherwise, you have substantial residuals and there might be something going wrong. So if you assume white noise, or chi-squared independent noise, you're assuming a covariance matrix that has elements only along the diagonal. And if you generated a bunch of random white noise, it would look something like these draws here, where they're not the right amplitude, nor have the right covariance structure to actually match the residual on the bottom. Just to bring that home, here's the 1 in 3 sigma contours of many draws. So what we did is developed a modification to this likelihood that actually introduces covariant noise at the locations of discrepant spectral lines. And when you make draws from this covariance matrix, you can see that now both the amplitude and the structure of the noise is what well replicates actual residual structure. And so this gives you better understanding of the uncertainties on your stellar parameters without biasing yourself by incorrect noise models. And so just to bring the point home, here's the 1 in 3 sigma contours, where now that discrepant spectral line has essentially been downweighted by this increased noise specific to the location of that spectral line. Just to wrap up, so my thesis work has been designed around determining the stellar properties of a sample of stars that we can both measure their properties like how hot they are and their radius using the optical spectra. And then we can go in, so for example, that's the top panel where these are again the same models that predict how stars evolve as a function of mass. And then these models also predict mass. So using our disk-based dynamical techniques, we can actually go and measure the mass empirically and see how well these models stack up. So here's a fit for 4 different pre-main sequence model evolutionary tracks and our dynamical mass measurement. In this case, it actually agrees quite well because this is a older F star where the models do fairly well. So my thesis work, as I mentioned, is determining the properties of this sample of about 20 stars where we have interferometric radio data and high-resolution optical spectroscopy. And I hope to learn something about the early stages of stellar evolution. Thank you very much.
We have time for a few questions.
So you mentioned your model can constrain the stellar mass of young stars. How does your model constrain the age of young stars? It's a relevance.
Yeah, you'll notice there's no bar on the age direction in this graph. So that's mostly done through more traditional techniques. In this case, the age that you determine from the models actually agrees quite well with, say, the cluster age. But that's true, we don't have actual constraint on that.
Sort of a similar question. Can you talk about the influence of metallicity on getting the temperatures and radii? Do you just marginalize over it, or do you fit forward? Or?
So most of these are believed to be around solar metallicity, so that's not as big an effect. So they're not extremely metal poor, for example. But it's a parameter that we fit for, and yeah, it's consistent with what you'd expect for these images. I think John will talk a lot more about the nitty-gritty details of that.
You were able to narrow down any particular set of pre-main sequence evolutionary tracks that data best matches?
Well, in this case, you can see, I think Gartner does pretty well, but the focus of my thesis is not actually to pick a winner. Rather, it's actually to deliver a set of calibration standards for this. So traditionally, eclipsing binaries would be used, but the problem with those is that they're extremely rare. And so now with this disk-based techniques, you can actually measure the mass in a single, say, 30-minute ALMA observation, no monitoring campaign required, and now you can amass a very large sample of empirical dynamical masses before you had to go to eclipsing binary.
One more question.
This is sort of a follow-up question. Are your dynamical masses well enough constrained to start answering questions about age spreads in clusters if you start using your mass as a prior on the astrophysical?
I think it depends on what stage of the evolution, like what cluster you're studying specifically, and what distribution of stars are. And if you manage to choose them at a kink, a nice kink in that those tracks where you can actually get a orthogonal to the age spread, then yes. Thank you very much.